Hollow spirals can add a touch of elegance to your next project. They will also make a lot of people wonder exactly how you did it. The theory is quite simple to understand, however, when put into practice, it's a little more difficult than it looks. But if you will follow a few simple guidelines, you will easily be able to mill the style shown here, plus many others of your own design. We'll begin by explaining the basic theory, and then we'll expand on some of the tips and techniques that we of Phantom Engineering have learned the hard way. A hollow spiral is a little deceiving. It appears that a hole was drilled down the center to start with, but you can actually start with solid stock and mill the center out as you cut the spiral. It works like this. Using a long cutter, simply plunge down, making several passes until you have cut to the center of the stock. Now you need at least one other start that also cuts to the center. These two cuts will meet in the middle and automatically mill out the center core. It's that simple. A second technique is to start with a column that is already hollow. There are several ways to do this as well. You could take a solid piece of wood and drill a hole down the center, or you can use a material such as flowstone that can be poured up in a tube with a smaller tube in the center as shown here. Being woodworkers, the first material we all think of is hardwoods like oak, cherry, maple, or mahogany. But there are a lot of other materials that also work very well, which we'll talk about in just a moment. When using wood, you need to be aware of a few potential problems. First, wood has a grain that makes it strong in one direction, but very weak in the other. If you look at this spiral piece, you can see that the grain is now very short. When milling a hollow spiral, you are actually making a large wooden spring which will flex and bend. The softer the wood, the more it will spring. This creates two problems. First, as soon as you cut out the center of the stock, if you have too much pressure from the tailstock, you will compress the spring and the actual path of the cutter will change. If you try to make another pass, it will not cut exactly the same. The second problem is that because the splines are weak and can compress, they will also vibrate and the piece can explode right in the machine, which I guarantee will ruin your day. So for the best results when using wood, remember to use a hardwood, preferably with a closed, even grain like maple. Watch that you don't put too much pressure from the tailstock and mill the last pass very slowly. One way to avoid the problems associated with the grain of the wood is to use a different type of material, such as MDF. This material mills well, and because it has no grain, is a little easier to use. However, the only option that you have when it comes to finishing the piece is to paint it. A new product on the market that we are quite excited about is Environ. It's a new solid surface material that cuts, mills, glues, works, and finishes like wood, but looks like stone. Like MDF, it has no grain and is very strong, eliminating most of the problems associated with wood, but it gives you more options than MDF when it comes to finishing. Currently it is available in 6 different colors. Other solid surface materials are available, such as Corian and Gibraltar. Most of these materials need to be laminated and then milled to a round. Flowstone, on the other hand, can be poured up in a round with a hollow core, eliminating a lot of the work and cost. It's also very strong and heavy. If you use your imagination, you will find other materials that will work equally as well. As we saw when using wood, the spiral cut makes the length of the grain short, which weakens the part and makes it flex like a spring. The best way to add strength is to set the pitch as long as possible. Set the gears for a 12 or 15-inch pitch if you have the 2 times gear set, or to the 7.5-inch pitch if you only have the standard gear set. The number of starts will also determine how strong or weak the part is. As we mentioned before, you need at least 2 starts to hollow out the center. Just remember, the more starts, the weaker the part. You should also try to keep the hollow portion of the part as short as possible. As the splines get longer, the more they will flex and vibrate, and the more likely they are to break. The larger the diameter of the stock, The thicker and stronger the splines will be. However, if you are milling a solid piece of stock, the radius will be limited to the length of the router bit. If you are milling stock with a hollow core, then you can go much larger. To cut through the stock, you can use a straight or spiral cutter up to about 1 inch in diameter. A straight cutter is less expensive but creates more vibration and chatter as the bit cuts the material with a chopping action. A spiral cutter does a better job because there is always at least one point of the cutter making contact with the material, so you have a constant shearing action. It will also lift the chips up out of the groove. We recommend a 2-flute spiral upcutting router bit. Several sizes are available from Magnate. For best results when milling hollow spirals, remember to choose a strong material. Set the pitch as long as possible, use no more than 4 starts, keep the diameter of the stock large, the length of the hollow section short, and use a 2-flute spiral cutting router bit. Following these guidelines, you should be successful on your very first attempt. Using the information we just discussed, let's design a typical sample piece. We'll begin by using hard maple, milled to 3 inches in diameter. Next, we set the spiral drive to a 15-inch pitch and using a 1/2 inch diameter 2-flute spiral upcutting router bit, mill a 3-start hollow spiral approximately 16 inches in length. It's as easy as that. Once you have mastered these basic techniques, you may want to experiment and create your own style. A hollow spiral tends to be a little fragile. Therefore, the order in which you perform certain operations is important. The very first step is to mill the stock round and then sand out any marks left by the router bit. Next, mill all of the accent cuts like circular molding, especially any cut that will be on the spline. And finally, after everything else is complete, mill through to the center on each start to create the hollow center. Now that we've covered the basics, we'll show you how to mill each of these sample pieces, step by step. For the first sample, we started with a solid piece of poplar, 2 1/4 by 2 1/4 by 18 inches long. We set the pitch to 3/4 of an inch using the .25 gear reduction set and the 60-tooth drive gear, and milled the stock round using a 1 1/4 inch diameter surface planing bit. Normally, we would cut off the corners on the table saw first. However, in this case, the blank is small enough that we just milled it round in 2 passes. Notice how the dust collector contains almost all of the sawdust. After the first pass, we used a set of calipers to check the diameter at each end of the part. If there is a difference, you can make a slight adjustment to the bed as shown in the Fast Start training video. With the adjustable bed set level, we finished milling the stock round. This last pass gave us a smooth surface, but we could still see the spiral path left by the router bit. Using 120 grit sandpaper, we sanded out the router bit marks. When all of the marks were removed, we finished sanding with a 220 grit paper. Next, we milled the circular molding at both ends of the workpiece, as well as the spiral decorative cuts. The 4 right-handed spiral accent cuts were milled 8 inches long, with the gear set for a 7.5 inch pitch. We then changed to a left-hand spiral and milled the 4 hollow spiral cuts using a 1/2 inch diameter 2-flute spiral upcutting bit. We plunged the bit down and milled approximately 3/8 of an inch with each pass. When the carrier tray reached the micro switch stops, we plunged the bit another 3/8 of an inch, reversed the direction of the motor, and milled back the opposite direction. We then repeated this process until the bit cut to the center of the stock. This style has 4 starts and only a 7.5-inch pitch. Therefore, you must mill the final pass very slowly to avoid breaking out the splines. You will also want to keep the length of the spiral section short, especially when made out of wood. When the first start is complete, we released the tailstock and rotated the workpiece 90 degrees for the next start. We then repeated the whole process over again until we had completed all 4 starts. The accent spirals cut in one direction and the hollow spirals cut in the opposite direction. We created a basket weave effect. The final step was to sand all of the edges and clean up the part. The next piece we made out of flowstone. The center was hollow, so we needed to make a wooden plug for the live center. Using a surface planing bit, we simply milled the end of a piece of wood round. The diameter of the stock had to match the diameter of the hole in the flowstone. First, we milled the end slightly oversized, and then test fit the piece and made adjustments to the plunge depth until the plug fit snugly. Then we cut the end off and marked the center. This part now slides into the end of the flowstone for the live center. To secure the workpiece at the headstock end, we removed the index drive center and replaced it with a 3-jaw chuck. By closing the chuck, we were able to insert the workpiece into the machine. The jaws of the chuck slid into the hole in the end of the stock, while the live center supported the opposite end with the block we milled to stop the hole. After closing the quick-release stock, we opened the jaws of the chuck to center and secure the workpiece at the headstock end. Using the .25 gear reduction set and a surface planing bit, we milled off about 1/16 of an inch to ensure that the part was round and smooth. We then changed to the 2x gear reduction set and the 32th drive gear to give us a 12-inch pitch for the spiral cuts. We decided to use a dish cutting router bit to mill a wide spiral flat to accent the hollow spiral grooves. When milling hollow spirals, the router generally is set to the center of the workpiece and held stationary with the router stops. After setting the microswitch stops at the desired location, we set the plunge depth for approximately 3/16 of an inch to mill the spiral flats. We then plunged the bit into the material and cut from the tailstock to the headstock end. Actually, it doesn't really matter which end you start milling at when you have the dust collector attached, but for best results, you should remember to turn the shop back on. You can see how the inside corners of the flat have a small radius, which is formed by the dish cutting bit. On this part, we could not index 90 degrees for the next start by releasing the tailstock and rotating the workpiece because we are using the 3-jaw chuck. Instead, we used another method that works equally well. First, we open the split nut and then move the carrier tray 4 inches, which is 1/4 of the 12-inch pitch, or 90 degrees. We then close the split nut to hold the carrier tray in place. By measuring the distance from the end of the top rail or by counting the number of threads on the linear drive screw, you can index for the next start without removing the workpiece from the system. Next, we drove the carrier tray back to the microswitch stop at the tailstock end to begin the next start. We then repeated the same process for all 4 starts of the flat spiral cut. Here you can see all 4 of the spiral cuts. The next step is to mill the hollow pass right down the middle of each of these flats. To do this, we used Magnate's 1/2 inch diameter 2-flute spiral upcutting router bit. Not only does it give us a very clean cut, it also lifts the flowstone powder out of the groove so that the bit doesn't heat up. The machine is already set up to mill the hollow spirals because they are milled in the exact same position as the spiral flats. When milling the flowstone, we milled approximately a 1/4 of an inch on each pass. When the carrier tray reached the microswitch stops, we plunged down another 1/4 of an inch, reversed the motor direction, and pushed the override switch to mill back the opposite direction. We recommend that you lock the split nut closed so that it does not inadvertently come open while milling the spiral and ruin your part. It took us 4 passes to mill through to the hollow core. Using the same indexing technique as we used to mill the spiral flats, we milled the other 3 hollow spirals. We found this material to be extremely strong and decided we could have made the spline smaller so that we could see more into the hollow center. For the next sample piece, we glued up 4 1-inch thick pieces of Environ to make a 4-inch by 4-inch by 22-inch long blank. We then cut off the corners in the table saw and mounted the index hubs as shown here. We then changed to a 1-inch diameter 2-flute straight cutter. Using this cutter, we milled the stock to a round in 1 pass. For best performance, you should only offset this bit approximately a 1/4 of an inch because the diameter is smaller than the surface planing bit. For this piece, it really didn't matter how smooth it was because the surface all gets milled away. Next, we changed to Magnate's 2-inch diameter roundover bit with a small radius at the point. And once again, we centered the bit for milling the spiral. We then set the microswitch stops at each end for the desired length of the rope section. After setting the plunge depth, we plunged the bit into the material approximately 1/8 of an inch short of the final plunge depth and made the first pass. We set the spiral drive to a 12-inch pitch using the 2x gear reduction set and the 30-tooth drive gear. We wanted this spiral to be fairly loose. When the carrier tray reached the microswitch stop, we plunged the router bit down to the final depth and milled the final pass in the opposite direction. Normally we like to mill spiral cuts all in the same direction, but this technique worked well and saved us a little time. To index for the nick start, we first turned off the motor drive and then measured the distance from the carrier tray to the end of the top rail. We then opened the split nut and moved the carrier tray 8 threads, or 2 inches, which equals 1/6 of the 12-inch pitch. We also double-checked the measurement to be sure we didn't miscount the threads. After returning the carrier tray back to the starting position of the rope, we again plunged the bit into the material and milled the second start. We then repeated the same operation 4 more times to complete the rope section. For this piece, we wanted to make a 6-start rope and then mill out every other bead. By milling the rope first, the splines are already round before we start milling the hollow section. Next, we indexed the part and milled a pass on one side of the bead and then a second pass on the other side of the bead. The indexing procedure is as follows. For the first pass, we moved the carrier tray just 1 thread and locked it in place. This offset the bit just far enough to mill against one side of the bead. Then, using a 1/2 inch diameter 2-flute spiral cutter, we made several passes until we had cut to the center of the workpiece. For the second pass, we moved the carrier tray 6 threads, or 1.5 inches. Remember to turn off the motor drive before you open the split nut and move the carrier tray. If you don't, the motor will rotate the workpiece when you move the carrier tray off the microswitch stop. This second pass mills out the other half of the first bead. For the third pass, we moved the carrier tray 10 threads, or 2.5 inches, to begin milling out the second bead. After we had completed this pass, we alternated between 6 and 10 threads for the rest of the splines. This procedure will mill out every other bead, leaving the 3 splines. Here you can see how we milled on one side of the first bead, and then by moving the carrier tray 6 threads, we milled on the side of the second bead. We then indexed 10 threads to set the router bit on the far side of the second bead, followed by 6 threads to begin the next bead, and so on, repeating this pattern until all of the splines were completed. After the hollow portion was milled out, we came back and milled the ends round and dressed up the ends of the splines. For the next sample, we chose to make a contoured profile with a hollow spiral. We began by mounting the template base onto the machine with the hardware supplied with the contour duplicator package. We then inserted a 4.5 inch by 4.5 inch by 24 inch block of MDF, which we had glued up using 6 pieces of 3/4 inch material. We had already laid out the profile for our template and traced it onto the top surface of the MDF. By rotating the workpiece until it was level, we were able to align the bit to set the template. By making marks every 1 inch along the profile, we were able to set the bit at a point on the workpiece and then position the template to match. When the template was properly aligned, we clamped it temporarily in place. We then repeated this step at the opposite end and then checked the travel of the bit to ensure that it followed the line. Here you can see how the stylus or roller on the router base lines up with the template at the same position as the router bit is on the workpiece. Next, we drilled up through the template base to mark the alignment holes on the bottom of the template. A series of holes were already drilled in the template base every 3 inches apart. We marked every other hole in the bottom of the template. We then removed the template and turned it over to drill the mounting holes from the bottom. Two-inch cap screws and wing nuts were used to mount the template to the template base. The head of the screw had to be low enough to clear the router base as it passed over the top. We then removed the workpiece from the machine and cut off the 4 corners on the table saw. For this operation, the bed must be level and raised as high as possible without the workpiece hitting the bottom of the carrier tray as it rotates. To mill the contour, the bit must cut from the side of the stock instead of from the top. We set up and used the spindle motor to rotate the stock without driving the linear drive screw. You can also rotate the stock with the linear drive motor if you don't have this optional spindle motor. The workpiece was then milled round by rotating the stock and manually sliding the carrier tray from one end to the other end while the router followed the template to create the profile. With this design, we're not real concerned with how smooth the surface is because it will be removed when we cut the spiral flats. Next, we engaged the 2x gear reduction set and the 24-tooth drive gear to give us a 15-inch spiral pitch. A microswitch stop was set at each end of the template to control the length of the spiral flats. For this design, we didn't have a spiral cutter long enough, so we used the 2-flute straight cutter instead. Next, we moved the roller out approximately 3/16 of an inch to mill the 6 spiral flats into the round cross section. We then slid the carrier tray back to the tailstock and engaged the split nut. Then we drove the carrier tray back to the microswitch stop to begin milling the first pass. When the carrier tray hits the stop at the headstock end, we simply reverse the direction of the motor and mill back to the tailstock for a cleanup pass. To index for the next start, we open the split nut and move the carrier tray 10 threads, or 2.5 inches, which is 1/6 of the 15-inch pitch. Again, be sure to turn the motor off before you open the split nut and move the carrier tray. Now we simply repeat the same milling procedure for the second spiral flat. The one thing we found with MDF is that you should really use the dust collector attachment if at all possible. The sawdust is really fine and very messy. After 4 more starts, we ended up with a 6-sided spiral twist that followed the template. Again, remember to turn off the motor drive before you open the split nut to index for the next pass. To mill the hollow spirals, we index the workpiece 90 degrees by moving the split nut 15 threads, or 3 3/4 inches, which is 1/4 of the 15-inch pitch, or 90 degrees. Next, we remove the template because the hollow spiral cut is actually straight down the center of the workpiece. We then positioned the router bit at the center of the stock and locked it in place with the router stops. Then we set the microswitch stops for the length of the hollow section. With MDF, we found that we could mill a little deeper with each pass than we could with the flowstone or the wood, but the process is the same. Mill from one end to the other and then plunge down a little deeper and mill back to the beginning until you have cut to the center of the stock. After the first pass, we knew that a dust mask and glasses were mandatory when working with MDF. For the second hollow spiral cut, we moved the split nut 20 threads, or 5 inches, which is 1/3 of the 15-inch pitch. We then repeated the whole process for the third hollow spiral cut. And finally, we changed to a 2-inch diameter core box bit and set clamps on the top rails to hold the carrier tray stationary while we milled a cove at the bottom of the spiral section. This procedure is also shown in the Fast Start training video. For the last sample, we chose a very simple design and decided to use flowstone because of its strength. Again, we used the wooden plug for the live center and the 3-jaw chuck to hold the workpiece in place. The gears were set at a 3/4 inch pitch, and we used a surface planing bit to mill off just enough material to ensure that the outside surface was round and smooth. We then set the gears for a 15-inch pitch and milled from the side of the stock with a 2-flute spiral cutting router bit, just like we did with the contoured profile, but without using the template. Next, we indexed the stock 180 degrees and milled a large flat on the opposite side. This left us with a round piece of stock with 2 parallel flat surfaces that spiraled around the stock. We then indexed the workpiece 90 degrees and set the router stops 1 inch apart. This allowed us to mill a slot 1½ inches wide through the flat sections by moving the router from side to side. What was left was a hollow spiral with 2 wide bands and lots of space in between. The last step was to remove the PVC tubing from the center of this piece and cut it to length. In this video, we've shown you just a few ideas for creating hollow spirals. The possibilities are almost endless. With a little imagination in your woodchuck, you can create projects that others can only dream of. Whether you're a hobbyist who wants to make small projects that have a distinctive flair, a designer who wants to create fine furniture, or a builder who wants to build architectural components that really make a statement, the woodchuck can help put you in a class all your own. At Phantom Engineering, we know that your success will ensure our success. Other videos that are now available will show you step by step how to build projects like the pieces in the southwest bedroom set. Look for other instructional and project videos on architectural components and projects, as well as fine furniture and craft items. If you are interested in the materials that we have used throughout this video, such as the flowstone, Environ, or Corian, please call our customer service department. In addition to training and project videos, Phantom Engineering also produces professional color brochures that you can use to promote your business. Each brochure has a blank box for you to print your company name, phone number, or promotional. Call Phantom today for details and pricing. Hey, always remember to wear the proper eye, ear, and breathing protection whenever you're operating the Woodchuck multi-axis milling system. These things won't do you a bit of good hanging neatly on the wall. The Woodchuck is the most versatile milling system available without going to the expense of CNC machines. Now the Contour Duplicator adds a whole new dimension to your system. In this video, we will illustrate several different styles and milling techniques using a single template. We will walk you through step by step the setup and milling processes used to create these 5 sample pieces. You can then use these techniques to design and build your own projects. The Contour Duplicator is similar to a copy attachment for a lathe in that it allows the router to follow a template to mill a profile. The biggest difference is that the Woodchuck uses a router bit and not a gouge. Therefore, intricate details such as the beads and coves are added after you mill the general profile. The Contour Duplicator allows us to mill round components like the sample shown here. Using a copy lathe, we could also turn parts similar to this one very quickly and accurately. However, when using a lathe, this is all you get. With the Woodchuck, the possibilities have just begun. The first thing that you'll notice is that the parts don't have to be round. They can be indexed with as many surfaces as you like. For this sample, we used the same template as before, but we indexed the workpiece to mill 8 evenly spaced surfaces. Again, using the same template, we chose to mill 8 surfaces. Only this time they are not evenly spaced. We simply changed the size and angle of the surfaces. And this is just one simple variation of the indexing techniques that are available. You can also combine the spiral drive with the contour duplicator like we did for this sample. The number of starts, pitch, direction of the spiral, and the router bit can all be changed to create hundreds or even thousands of variations. Here is a totally different look using the same template and the spiral drive. It's obvious that the possibilities are almost endless. In a moment we'll show you step by step how to set up and mill each of these 5 components. After that, we want you to experiment and see what you can create. Remember, the best part of owning the Woodchuck is that you can really stretch your imagination. And besides that, it's just a lot of fun. Most of the milling operations on the Woodchuck are from the top of the workpiece. However, when using the contour duplicator to mill a profile, use a long router bit and cut from the side of the stock as shown here. A few limitations that you'll want to keep in mind is that the bit has to cut at least as deep as the radius of the stock, and that the router bit movement is restricted by the rectangle hole in the carrier tray. When milling from the side, you can choose from a selection of bits. The least expensive is a 1/2 inch diameter 2-flute straight cutter. For the best performance, however, we recommend a 1/2 inch diameter 2-flute spiral down cutter. The spiral cutters have at least one point of contact with the wood at all times, resulting in a clean shearing action. The down cutter will throw the chips down into the dust collector or onto the floor instead of up into your face. Both types of router bits are available from Magnate. They can also source custom router bits or even end mills. To use the contour duplicator, you first need to replace the standard router base with a base that has a roller. The roller acts as a stylus and follows the template. It can also be positioned to vary the size of the finished part. The next step is to build and attach the template base. The template base should be made from 3/4 inch plywood. The first step is to rip a piece 7 inches wide. Next, set up the saw to cut a second piece that is 1.5 inches wide. This second piece is for the back edge of the template base and will help keep the base from flexing. Then cut both of these pieces to length. If you have the 80-inch system, cut them to 95.25 inches long. For the 56-inch system, cut them to 72 inches. And for the 33-inch system, cut them to 47.75 inches. Next, you'll need to cut a relief for both the micro switch that travels with the carrier tray and the stops that mount on the top rails. Mark this cutout starting at 3.5 inches from each end and 1.5 inches wide. After marking the cutout, drill a small hole in each corner. If you clamp a piece of wood underneath the plywood, the bit will not split out the back side as you drill through. You can make this cutout using a skill saw or a table saw. We chose to use the table saw and started by raising the saw blade and then marking both sides of the blade on the saw fence so that we would know where to stop cutting from the top side. We then set the fence for a 1.5 inch wide cut. Next, we held the board firmly against the fence and carefully lowered it onto the blade. We then backed up until the starting point for the cutout was even with the mark on the fence. And then slid it forward, cutting to the mark at the opposite end. We then used a handsaw to finish making the cutout. The next step is to lay out the hole pattern for mounting the templates. Start by making a mark at 3 and 4.5 inches from the outside edge on both ends. Then use a straight edge to draw the 2 parallel lines. Starting at about 5 inches from the end, make a mark every 3 inches. You can then use a square to lay out the holes on both lines. Drill all the holes with a 3/16 inch drill bit. We chose to use biscuit joints to attach the outside edge piece to the base and marked both pieces where we wanted the biscuits placed. We then cut the slots in the outside edge of the base and on the side of the edge piece. The biscuits will make a strong joint and also keep the edge piece flush with the top surface. Be sure to use plenty of glue on the edges, in the slots, and on the biscuits themselves. Then set the edge in place and clamp it securely for several hours while the glue dries. After the parts are tightly clamped, you can then wipe off the excess glue with a damp rag. Next, you need to attach the template base brackets on each end of the woodchuck opposite the linear drive screw, with the hardware provided as shown here. Then set the template base on the brackets and clamp it temporarily in place. Now check to see that the carrier tray does not hit the base at each end before proceeding. When the base is positioned correctly, mark the slot from underneath. Again, clamp a board underneath the template base to prevent the plywood from splitting on the top side, and drill a 3/8 inch hole at the end of the slot on each end of the template base. Then countersink the holes on the top side of the base for the 3/8/16 flathead screws. Now the base is ready to attach to the machine. Wing nuts are provided for the bottom so that you can quickly remove the base if you desire. The template should be made out of 3/4 inch stock. You can use about any type of material that you like. We have found MDF to be very easy to work with, and it sands up very smooth. Start by laying out the profile that you want to create onto the material and cut it out using a jigsaw or bandsaw. Then sand the template as smooth as possible. Any bump or dip on the edge of the template will show up on your finished part. There are companies who will cut out your templates using a CNC laser. The cost will be somewhere between $100 and $200. It's a bit pricey, but if you're doing production work, it could possibly pay for itself by reducing the amount of sanding on the part after it is milled. The template base can be moved in and out as desired. We generally position it as close to the rails as possible. Later, when we set up a template, we will know where to position the base each time we use that same setup. Also, make sure that the roller is positioned approximately in the center of the slot to start with. That way you can make slight adjustments in both directions if necessary. Now place the template on a square blank and trace the profile. Then make a mark at the center of both the template and the square blank. Line up the router bit with the mark at the center of the blank. Then slide the template until a corresponding mark lines up with the roller. Now align one end of the template and clamp it temporarily in place. Then align the opposite end and secure it in place with a clamp as well. Test the template alignment by sliding the carrier tray from one end of the template to the other. The router bit should track the line on the square blank. Now, using a 3/16 drill bit, drill up through the bottom of the base to mark the holes in the template. Then remove the template, turn it over, and finish drilling the holes. The template can now be attached securely to the base with 1032 by 2-inch machine screws. If you use wing nuts on the bottom, you can quickly remove or attach the template at any time. And finally, test the heads of the screws that they do not hit the router base. And now you're ready to start making parts. Because the first sample is a simple round part, we started by cutting the corners off on the table saw to save time as well as wear and tear on the router bits. We then mounted the indexing hub, leveled the bed, and inserted the stock into the system. On this first piece, we were going to mill the part directly to the template in one step. So we set the router bit against the side of the stock and positioned the roller against the template. But then we decided to mill the stock round first using the 0.25 gear reduction package as shown on the Fast Start video. That way we would have less material to remove when following the template. We turned the router around so that the roller would be out of the way, and then we set the stops for a 1/4 inch offset on the far side. Next, we attached the dust collector to the carrier tray, and then hooked it up to the shop dust collecting system. This accessory will help keep the air that you're breathing clean and save you a lot of time when it comes to cleanup. Several times during this video, we remove the dust collector so that you can see what is happening up close. If possible, however, you should use it all of the time. Not only does it contain the dust, it also makes the system safer to use because you can't get your fingers anywhere near the bit while milling. With the gears set for a 3/4 inch pitch, we used the 1 inch diameter 2-flute straight cutter to mill the stock round. For best results when using this bit, the router should be offset only 1/4 of an inch. The surface won't be as smooth as when using a surface planing bit, but it mills faster and will remove more material in a single pass. In this case, we really don't care how smooth the surface is, because it all gets milled away later anyway. Next, we change to a 1-inch diameter round nose bit to mill a cove at each end of the template. You will understand why we did this in just a moment. The cove should be milled right at the end of the template, so we simply turn the router back around and use the roller to locate the position for the carrier tray. For the next step, you can use either Jorgensen clamps or the micro-switch stops that come with the linear drive motor. Stops should be set on both sides of the carrier tray to hold it securely in place. Next, we had to remove the roller so that it wouldn't interfere as we milled the cove. We then set the plunge depth on the router. We also connected the Y-axis positioning screw to give us more control when making this cut. By plunging the full depth while the cutter is off to the side of the stock, and then bringing the bit over center as it turned, we avoided burning or making a divot in the workpiece. The cove was milled to the same diameter as the part will be at this point after the profile is milled following the template. Next, we used a 1-inch diameter point cutting roundover bit and positioned it so that it was centered on the outside edge of the cove. Again, we used the stops to hold the carrier tray in place as we milled the bead. After setting the plunge depth, we used the same milling technique as before to avoid burning the stock. We milled 2 passes 1 inch apart to form the bead at the end of the workpiece. Then we repeated this operation at the headstock end. When milling the profile, the bit will start and end in the coves at each end. Using this technique, you won't chip out the material at the beginning or the end of the cut. To mill the profile, we used the 1-inch diameter 2-flute straight cutter. We positioned the router bit so that the blade was touching the stock, and then set the roller against the template. You need to tighten the roller with the T-wrench so that it doesn't accidentally move when milling the profile. You'll also want to make sure the carrier tray and the bottom of the router base is clean. We even used WD-40 to keep the router floating freely in the Y-axis when following the template. We chose to use the optional spindle motor for the next step, You can, however, use the linear drive motor or even rotate the stock with the handle if you do not have either of the motors on your system. With the stock rotating as quickly as possible, you slowly move the router from the tailstock to the headstock end. Do not try to remove too much stock in a single pass. If necessary, make several passes removing a little bit of stock at a time until the roller follows along the template. After the stock is milled roughly to shape, you can make the final cleanup pass. This final pass should be made from the headstock back to the tailstock end. The slower you move the router, the smoother the surface will be. We used a palm sander to finish sanding the part while it was still in the machine. With the general profile completed, we set up to mill the details in the center of the part. We started with a 2-inch diameter core box bit. To mill the cove in the center of the part, we simply made a mark on the template. Then we removed the roller and used the slot in the router base to position the carrier tray. Rather than trying to calculate exactly how deep to cut, we simply marked how wide we wanted to mill the cove. Then we plunged down deeper than we actually needed and slowly brought the cutter over the part until the cove was the correct width. To mill the beads on the side of the cove, we opened the split nut and moved the carrier tray 5 threads. If you used the linear drive motor to turn the stock, you could not use the split nut for positioning. You would need to use clamps on the top rails like we did on the ends of the piece. Next, we changed to a 1-inch diameter point cutting roundover bit. Set the plunge depth for the cutter and milled the bead using the same technique as before. The last step was to move the carrier tray back 10 threads to mill the second bead on the opposite side of the cove. This is the type of part you could also turn on a copy lathe. However, with a lathe, this is about all you can do. With the woodchuck, the fun has just begun. For the next sample, we measured the blank to find the narrowest surface. We then set the plunge depth for this surface to ensure that we would mill the largest diameter possible without leaving any flat spots when we were finished. Then, using the same 1-inch diameter core box bit, we put the 40 position index plate on the spindle shaft to mill a cove at the beginning and ending points of the template. Only this time we indexed the part 8 times and milled across the surface in the y-axis. This took several passes to get down to the final plunge depth. To get the 8 evenly spaced surfaces, we indexed 5 holes for each side. This indexed cove serves the same purpose as before. It gives us a starting point for the router bit when following the template so that we don't chip out the wood. For the opposite end, we decided to try something a little different. So we replaced the indexing plate with the handle on the spindle shaft. At this end, we started by milling a round cove, but we didn't plunge down the full depth. Starting with the round cove turned out to be much faster than milling the deep cove using the indexing technique. To finish, we put the 40 position indexing plate back on and milled the indexed cove to the full plunge depth. We then used the same technique to add the indexed beads on each end using a 1-inch diameter point cutting roundover bit. Next, we positioned the roller on the template base to mill the stock following the template. But because we had so much stock to remove, we decided to start by milling the part round, but slightly oversized. We could have used a bandsaw to remove a lot of the stock before we started milling. You might want to try both ways to see which method works best for you. When there is a lot of material to mill off, you want to be sure to mill it in several small passes, removing a little bit at a time until the roller follows the template. Here you can see that we quickly roughed the part to the shape we needed. Notice that we didn't waste a lot of time trying to get a smooth surface. Next, we repositioned the roller to cut to the final depth. You'll want to tighten the roller with the T-wrench so that it doesn't move and ruin your part. Now, using the 40 position index plate, we set up and milled the 8 flat surfaces following the template. You can see that these passes only have a little bit of material to remove, but we still make the cut in 2 passes. The first is made from the tailstock toward the headstock, and the final cleanup pass is made back toward the tailstock. You'll notice here that we're using the linear drive motor to move the carrier tray. We could also move it manually, but using the motor gives us a lot more control. To mill the details in the middle of the piece, we removed the roller from the router base and then centered the router by lining up the base to the center mark on the template. Then we changed to a 1.5 inch diameter plunge style cove and bead or classic bit. For the first pass, we offset the split nut 6 threads or 1.5 inches. Then we set the plunge depth so the top of the roundover was even with the surface of the stock. Depending upon the size of the router bit and the wood you used, this may take more than one pass. Using the 40 position indexing plate, we indexed the part 5 holes, or 45 degrees for each of the 8 surfaces. With the first cove complete, we are ready to set up for the next cut. For the second cut, we moved the carrier tray 8 threads, or 2 inches. And then we repeated the same milling operation as before to complete the second cut. There is only one more step to complete this part. For the indexed cove in the center of the part, we used the same 2-inch diameter core box bit as before. We centered the carrier tray and milled the cove 1.5 inches wide on each of the 8 sides. This part is very similar to the first one, except it has 8 sides instead of being round. For the next sample, we'll also make 8 surfaces, only we'll change the angle and the width of the surfaces to create a very nice effect. For this part, we started with a blank 3 inches by 4 inches wide, and then laid out the profile on each surface. Then we cut the part roughly to shape using a bandsaw. This step will save you a lot of time milling off the excess material. For the coves at each end, we once again used the 1-inch diameter core box bit. Then we positioned the stock with the wide surface up and set the plunge depth. Instead of using the roller to position the carrier tray at the beginning and ending points of the template, we decided it would be faster and easier to mark the template at 1/2 of an inch from the end of the cut. Next, we slid the carrier tray up to the mark on the end of the template and locked it in position with the split nut. Then we indexed the part 2 holes off center. We also moved the router stops out of the way and then milled the first cove. This milling technique is used on both ends of the stock. The sequence is as follows. Mill the first cut 2 holes off center. Then mill the second cut 2 holes on the opposite side of center. When these 2 cuts are complete, index the part 180 degrees and once again mill a cove 2 holes off one side of center and 2 holes off the opposite side of center. Each of the 2 wide surfaces now have 2 angled coves. Next, we'll work on the narrow sides. First, we position the workpiece with the narrow surface up, and then reset the plunge depth. Again, we index the stock 2 holes on either side of center, and milled the remaining coves on both ends. We used the same technique to mill the indexed beads using a 1-inch diameter point cutting roundover bit to finish the details on both ends of the stock. Next, we set the roller and milled the surfaces following the template on the narrow sides. Again, each pass is made 2 holes off center. Again, we used the linear drive motor to move the carrier tray. If your system does not have this optional motor, you can also move the carrier tray manually. And just as before, the final pass should be made from the headstock back to the tailstock. Four of the 8 indexed surfaces are now complete, and we're ready to mill the final 4 sides on the wide surfaces. To do this, we simply index the part to 2 holes off center on one of the wide surfaces, and move the router bit up against the cove. Then we reset the roller to follow the template and locked it in place. Each of the 4 remaining surfaces are indexed 2 holes off center. This finished part has 8 surfaces, but is completely different than the first indexed part. After the profile is complete, you can add any type of decorative cut that you want. We chose to use a 1-inch diameter plunge style cove and bead or classic style bit. Each cove is milled 1 inch apart and indexed exactly the same as the flat surfaces. For the first spiral part, we began by milling the stock to a round approximately 3 inches in diameter. As you can see here, even when milling MDF, the dust collector will contain almost all of the sawdust. If you don't have the linear drive motor on your system, you can still use the linear drive screw and the handle to position the carrier tray for milling the coves at each end of the workpiece. Again, we centered the mark on the end of the template in the slot of the router base after removing the roller. We inserted the 1-inch diameter core box bit into the router and then plunged it onto the workpiece. Then we set the plunge depth for the cove just as we did before. All of the techniques in this video can be performed with the motors or manually as shown here, depending upon how your system is set up. Once again, we wanted to center the point cutting roundover bit right on the edge of the cove to mill the beads at each end. Because we did not use the linear drive motor to rotate the stock, we used a split nut to hold the carrier tray in place instead of the clamps. To move the carrier tray 1/2 of an inch, we simply opened the split nut and moved it 2 threads. The beads on the ends of this piece are identical to the first sample we milled, only the workpiece itself is a little larger in diameter. For the details in the center of this part, we decided to use a 2-inch diameter roundover bit. This bit is also available from Magnate. We set the carrier tray 1 inch off center, and again let the split nut hold the router in place as we used the handles to mill the bead. Next, we opened the split nut and moved it back 8 threads, or 2 inches, to mill the second half of the bead. With all the detail work complete, the last step is to mill the spiral flats following the template. For this step, we used a 1/2 inch diameter 2-flute spiral down cutting router bit. We decided to start by milling the stock round following the template. That way there would be very little material to remove when making the final spiral passes. So we positioned the roller and milled the stock round and slightly oversized. When the roller came to the middle section, we simply moved the router back and passed over the bead in the center of the workpiece, and then continued on to the end of the template. Now we were ready to mill the spirals. We repositioned the roller on the router base and then set up the gears. For this design, we chose to use a 10-inch pitch. This step is also done in 2 passes. The first pass is from the tailstock to the headstock, and then back to the tailstock again for the final cleanup pass. With the gear set for the 10-inch pitch, we decided to index the part for 10 spiral starts. Therefore, we opened the split nut and moved the carrier tray 4 threads, or 1 inch, which is, as you might have guessed, 1/10 of a 10-inch pitch. Here we have removed the dust collector so that you could see the part being milled. When the bit comes to the center, we simply push the roller away from the template to bypass the bead in the center of the part, and then brought it back to the template to mill the second half. For the last sample, we began by milling the stock round. Then we milled the coves and beads on each end of the workpiece, just like before. For the next step, we used a 1-inch diameter, 4-inch long straight cutter, also available from Magnate. We set the bit right against the inside of the cove. After positioning the router, we set the stops on the carrier tray to hold it in place. Then we set the gears for a 15-inch pitch and milled a spiral flat from end to end. Because of the amount of stock we had to remove, it took several passes to complete this cut. We used the Y-axis positioning screw to control the amount of material that was milled with each pass. Notice that this cut is straight. That is, it does not follow the template. When the first spiral flat was finished, we opened the split nut and moved the carrier tray 7.5 inches, or 30 threads, to index the part 180 degrees. An easier method may have been to simply lift the quick release handle on the tailstock, rotate the workpiece 180 degrees, and reinsert it into the machine. We counted the threads and measured the distance to double-check the positioning of the carrier tray. Then we backed the carrier tray up to the starting point at the tailstock end to mill the second spiral flat. Again, this step will take several passes to complete. This will create two parallel surfaces that twist from end to end. Next, we disconnected the Y-axis positioning screw and then set the roller to follow the template. Then we indexed the part 90 degrees by opening the split nut and moving it 15 threads, or 3 3/4 inches, which is 1/4 of the 15-inch pitch. The last step was to mill the edges of the parallel surfaces following the template. When we completed the first edge, we again used the split nut to index the workpiece 180 degrees and finished the opposite edge. At this point, we decided to leave this part just the way it was and not add any type of details in the middle of the part. In this video, we've shown you just a few ideas for using the contour duplicator. The possibilities are almost endless. You probably have ideas of your own. The secret is to experiment and use your imagination. Then you can create projects that others can only dream of.